So welcome everyone for today's webinar on where our Master Prize winners will present their master's thesis for which they received the prize. So we will start with Caroline Heitmann, who did a project on the evaluation and retrofit of a seismically damaged historical masonry building on the parish church in Pokupsko, Croatia. Caroline did this work in under supervision of Igor Tomic and Katrin Bayer and received the EPFL Master Prize for it. And then followed by it, we will have presentation by Mario Eugster and Janik Fürst from who received the Master Prize ETHZ. Well, I mean, maybe formally, so to say, because Janik had finished. It's Mario Eugster is our Master Prize winner, but it was a collaborative project. And they will present the analytical modeling and experimental vibration testing of a novel tuned mass damper on a scaled wind turbine. And they wrote their thesis under supervision of Eleni Hatzi at ETH. And with that, I think I'll pass the mic, so to say, to you, Caroline, and you can start the presentation. Sorry, one more thing I forgot. If you have questions during the presentations that you want to ask after, so we have the two presentations and can take questions after, but feel free to write any questions that you might have in the chat during the presentation already. Sorry.
So can everyone see my screen? Okay. Full screen. Okay, maybe not. I'll just hide this up. Okay. So as we discussed, today I'll be talking about an evaluation and retrofit of a seismically damaged historical masonry building. And before I get started, I just want to thank the SGEB committee for honoring me as one of the recipients of this prize, and just in general supporting young engineers and young students in this work, because it's super important. So thank you. And we'll go ahead and get started in presentation. So after a brief introduction, there'll be three main chapters. First, a discussion of out-of-plane mechanisms, specifically their identification and analysis, before talking about finite element modeling, and then going into rehabilitation proposals. Okay, so to introduce the project, we are talking about the Parish Church of the Annunciation of the Blessed Virgin Mary in Pokupsko, Croatia, which is a bit south of Zagreb. It was constructed in the mid-1700s, with its main materials being stone masonry for the body of the church, brick masonry being the vaulting systems, and a timber roof structure. And what is really unique about this church is that the domes are actually, or the vaulting system is elliptical, and there's these transitional triumphal arches in between the domes, as you can see here, if you can see my mouse. So this church was reconstructed at several points throughout its history, primarily just due to other damage, other earthquakes in the early 1900s, and also specifically during the Homeland War, which took place in the early 1990s. So during this, there was a grenade that went off, and so you can see in this photo the bell tower was heavily damaged, and also the vaulting systems were damaged, which led to their reconstruction in that time period. But so speaking more recently, in late 2020, there were two earthquakes in Croatia, and specifically on December 29th, there was a moment magnitude of 6.4 earthquake, with the epicenter about 22 kilometers away, I believe, from this church. And so this earthquake was quite devastating to the region, and it received a Category 4 damage, which is it's heavy structural damage and very heavy non-structural damage, which really motivates a lot of renovation work in this region, and specifically for my church. So looking now at the spectral accelerations, obviously they're measured closer to the epicenter, using records that were published, and then I scaled these peak ground accelerations to my actual site, and I will be using these in my analysis throughout the thesis. Okay, so moving on to our first chapter, the out-of-plane mechanisms, I'll be focusing on three main parts of the church: the bell tower, the apse, and the transepts. So out-of-plane mechanisms are very common during seismic events, obviously. And so a lot of the most common overturning mechanisms have been categorized in various abaci, and formulae for them have been developed. And so I will make a reference to a lot of these commonly seen mechanisms within my specific case study. So starting with the bell tower, first we do a visual analysis. So we can see some of the cracking that's noticed on the bell tower, specifically these long cracks that extend from the top window down to the bottom window, which is a very classic mechanism that's going to happen as the stress will divert around the windows into the more rigid column corners. And the middle part of the bell tower is left to much more susceptible to out-of-plane movement. And you can also see some cracking more horizontal in the kind of intersection with the body of the church, which is going to kind of be some of that pounding motion, as you can see in this rightmost image for the abaci. And so this kind of correlates with some of the mechanisms that we'd expect to see in the bell tower. And so using this geometry, we can then develop some equations that just formulate all the main forces to see what our lateral force capacity is, to see how much we need to overturn these bodies. And then we can use this data to plot pushover curves, which are the force displacement relationships, as well as our horizontal multiplier as a function of displacement, which is going to, again, correlate the lateral force necessary to overturn this proportional to its gravitational acceleration. And so looking at this further, we can use the N2 method to normalize our two elements, our two bodies in the two different planes into an acceleration displacement response spectrum, which is going to relate our acceleration displacement together. And then with that, we can plot our capacity curve to determine where our mechanism in question relies relative to its demands. So we can see here with the orange capacity curve that actually we're right around our force capacity. And so this indicates that we are meeting the displacement capacity for this overturning mechanism. So in other words, due to the in-plane wall, so just to be clear, by the way, when I draw this mechanism, it's actually two walls moving around the corner, the rotation around this origin point here. And so when you have those two walls in two different planes, the in-plane wall is going to really stabilize this mechanism. And so that is why we're actually able to increase our displacement capacity. And while we're going to experience damage in this bell tower, we're not going to have a complete overturning of the flexural mechanism. So moving to the apse, again, looking at this visually first, we can see a lot of cracking at the top of the wall that kind of extends down from the window in these like diagonal cracks, which is reflected also in our abaci, which is very encouraging. And so the reason that it's going to be so susceptible to fissuration at the top is because those vaults are really supported on these walls, and the thrust of the vaults are going to be pushing out this wall pretty significantly. And so with this in mind, we can draw our geometry. And I simplified this a bit because, as you can see in the apse, it's really curved walls, and that geometry is quite complicated. And so by simplifying it down into these more rectangular bodies, we can more easily understand our mechanism. However, what's unique about this mechanism is that not only is it going to be rotating around the z-axis, so vertically, but also horizontally around the x-axis. And so to address this, I use the principle of virtual displacements to sum my internal and external work. So my internal work are going to be my stabilizing forces. My external work is going to be my destabilizing forces. And together we can determine our horizontal multiplier again, and we can plot once more our ADRS with its capacity curve. And once again, the force capacity is met. And so that indicates that it is not a risk under these accelerations that we can hypothesize that could completely overturn out of plane. And then moving to the last part of the church that I studied for out-of-plane mechanisms, the transepts have very similar geometry to the apse, with these domed walls kind of at the edges that are going to contribute to a thrusting motion out of plane, with again these windows that are going to cause a stress flow and kind of highlight the vulnerability around the windows. And so again, I use the same kind of approach to formulate my out-of-plane equations for this part of the church. And we get similar results with our relationship between lateral force and acceleration, and also our capacity curve. So now moving to finite element modeling. So I'll first present some of the material properties that I used and how I calibrated my church model before going into some of the results that we can find with this approach. So one thing that is super interesting about this church is that actually it's being studied, well, it was studied and rehabilitated by a local engineering firm in Croatia called Studio Arhing, which actually does a large body of work in Croatia, which is very important. So part of their analysis is that they conducted materials investigative testing. And so you can see at the top here some of the results that they got from this investigative testing, which shows that the material property is quite low, especially compared to some materials that we use nowadays, but also just for this unreinforced stone masonry from nearly 300 years ago. And so what I did, because these material properties were rather unstable also in the modeling software, I referenced some literature, and then I also looked at what Studio Arhing was using as their values and decided to use this bottom table for my model properties, which were much more stable. In terms of the material laws that I was using in my modeling process, I used the concrete damage plasticity relationship, which is very important for masonry, which will have damage after it's yielding, and to kind of capture some of this fissuration, especially in the tensile rupture. And so we're obviously going to have much higher strength of compression versus tension. And so some of these properties on the right also help to calibrate this plastic behavior. And these properties I found throughout my thesis were very sensitive in the software. So it's super important to really calibrate your model well and kind of identify some of the sticking points of this rather important material property or material law. And so as I mentioned with tensile behavior in particular, I used the stress strain relationship for a weak mortar and then used fracture energy to calculate my displacement at the yield stress for a post-cracking mechanism. So now looking at the model itself, obviously the walls are rather simple to model. The bell tower, because of its reconstruction at various points in its history, actually goes from around almost 2 meters actually of thickness at the base to a mere 80 centimeters of thickness at the top. So to capture this, I stratified the walls of the bell tower, and then I did a complex vaulting system for the vaults, which, as I mentioned, was quite intricate because of these transitional arches, as you can see on all 4 sides of the main ellipses, and then the 2 northern and southern parts of the smaller dome. And so this actually caused a lot of problems with the meshing, just because you have some pretty fine points. So it's really interesting to kind of interpret some of these old style churches into like a modern day model. So first I did a modal analysis, and I isolated actually the behavior of the bell tower because I was interested in seeing what its behavior would be on its own versus as part of the whole church. Obviously, the bell tower now will be completely removed from the church, but I still thought it'd be interesting to kind of look at this behavior specifically. And so we can see that, as we'd expect, the first couple modes are very simple translational modes, while as we get into the higher modes, they start to get more complicated and form just more intricate shapes, also with some torsion acting. And then looking at the full church, we can see that our period is going to get smaller, which indicates that proportional to the bell tower, we have a much more rigid structure, which is what we'd imagine because the bell tower is rather slender structure, and so not very rigid proportional to its mass. But we can still see that in the modes of the church, the principal modes, the bell tower is very active. And so as we get into higher modes, the rest of the church body will be more activated. But it's just interesting that the bell tower is so present in the modes. And then I also did a quick response spectrum analysis just to get a kind of understanding of where we're going to see some of our stress concentrations. And so this is with respect to the Eurocode response spectrums for this region. And again, it just kind of gave me an area to look out for. So the bulk of my analysis was a pushover analysis. So with the force of the roof, I developed these force distribution equations that I then applied in the horizontal direction to push over my structure. And then now we're looking at some results in all the different directions. So starting with the bell tower once again, we can see that this graph on the or this plot or this image on the left shows the strains. And we can see a lot of strains near our windows in this front facade, which is exactly where we observed some of our cracks in the images earlier. And then also looking at our force displacement graph, we can see that after initial yielding, we really stabilize with displacement, which indicates that our weight is kind of redistributing as the hinges form. And this shows like the general quote unquote stability of the church in this direction, or sorry, of the bell tower in this direction. And then looking in a Z direction, so pushing into the bell tower, loading now, we also see some strains forming at the rightmost facade, which again is where we noticed a lot of cracking in our images. So once again, we can use the N2 method, and this time I'm really normalizing with my modal properties to find my effective properties to translate into this capacity curve. And it's important to recognize when the equal displacement rule is not applicable, and we have to use the equal energy rule specifically for our orange curve here. And so once again, though, our results are showing that we're within our displacement capacity requirements, which is reflected also by its compliance factors, showing that the bell tower obviously would not be isolated completely, but it is still meeting its stability requirements. Although I do want to point out the severity of the 2020 earthquake in the sense that its compliance factors are significantly lower compared to our 475-year return period. And then now looking at the church, looking in the positive X direction, I thought these results are very interesting, particularly here on the right transept, or sorry, the southern transept, I think it is, where you can see that this transition point between the two arches really buckled because there's no supports there and it's so much thrust, and so it's really a vulnerable area. And then as this buckles, the whole rest of the vault is pushed out onto this transept wall, and we have a lot of displacement, which is precisely where we've noticed a lot of our cracking in our images. So this goes to show just the vulnerability of this section in this region. And similar results in our other directions as well. Here you can see that the body of the bell tower is really stiffened by the rest of the body of the church, while the top of the bell tower is still free to displace, but you can still see a lot of buckling and stress concentrations at our transition points with our arches that are then going to be translated down to our walls. So for the N2 method, one thing that I considered for the church body was not just a global mechanism, which are going to be dictated by the principal of fundamental modes, but also local mechanisms that really capture some of that local behavior, as I mentioned, with this transit wall moving out of plane. And so I calculated my modal properties for the two mechanisms, but in the end, it was the global mechanism that more accurately captured the behavior. And so I used those to determine my bilinear curves. And once again, we can see that our intersections and our performance points are actually meeting the capacities, which again is reflected in the compliance factors. And so in general, the results show that while it is still within design, there's still going to be significant damage and factors that need to be addressed within the church, which led me to my rehabilitation proposal. So I will discuss some context and some solutions that the other engineering firm recommended before going into my personal proposal and analysis. So obviously with these historical buildings, the rehabilitation approach needs to be rather nuanced and holistic because there's a lot of other factors to consider, such as like the material properties changing over time, or also like the piecemeal reconstruction, as my church in particular has a lot of. And so these guidelines kind of help to orient yourself when going into these rehabilitation proposals. And so Studio Arcing actually proposed quite an extensive rehabilitation strategy. And so the day I actually visited, they were doing grout injections into the stone masonry walls, as you can see in this leftmost image. And they proposed also to construct a concrete ring beam around the main elliptical vault with this steel truss structure around, and also a steel truss structure in the tower. They also recommend filling in some of the masonry vaults with small wooden pieces that can kind of just make the behavior more cohesive in general. And so I considered this, but I also proposed some other designs. And so particularly with the nave, I thought it'd be most effective to use textile reinforced mortar, which has a variety of advantages, as you can see here. And so specifically, I recommend to apply it at the extras along the bottom part. And so you could theoretically apply it to both the intrados and the extrados. However, something with these historical buildings and rehabilitation proposals in general is that you want to minimize invasiveness. And in a church specifically, there is a lot of old artwork on the ceilings. And so obviously this would be hidden by the plaster, but it's super important to just consider this aesthetic purpose as well. And so it's also most efficient to put it at the bottom fibers, just to the way the thrust is going out through the horizontal fibers. And so this is a most, as I said, efficient use of materials while also maximizing its efficacy. And then in addition to this, just filling in some of those cracks that we can see highlighted in this leftmost image. Also still within the nave, so you can see here the wooden truss structure. And actually, it was in a bit of disrepair. There was some water damage. There were a lot of beams that were split, a lot of beams that were curved, no longer straight. Some beams were actually even connected to other elements and were kind of floating. And so I recommend that these are all addressed, and material or members that need to be replaced are replaced. And so part of my rehabilitation proposal is just to implement it also in my abacus model. So I did that by reinforcing it with these connector elements that kind of provide a more accurate capture of how the roof is going to be stabilizing or just rigidifying my walls as well with these connecting elements. Also in the bell tower, I propose constructing a small steel tower that I designed according to the SIA codes for steel design, and also including all of its seismic loading that I then can implement into my bell tower with these rigid constraints and these steel assemblies that I designed. And so looking now at the bell tower, we can see that within a pushover analysis, the retrofitted curve is the blue curve. And so we are already increasing our force capacity just by implementing this steel structure, which is very important. So looking at these two kind of approaches together, the roof elements and then also my steel structure in the bell tower, we can see that our force capacity is actually going to increase 7-fold for the same displacement compared to the unretrofitted church, which is very promising results. And just goes to show that these could be really helpful solutions. And so it's very interesting to consider how this kind of updated design can help our church. So that is my presentation. It was a very interesting project in terms of some of the struggles, with the modeling and trying to capture this old building and just, be nuanced with the approach, but also be realistic. And so, yeah, obviously there's a lot more work to do to contribute to this body for historical buildings all across the world. But it was very interesting. And thank you everyone for listening.
Thank you very much. It was very interesting.
Thank you.
So yes, as we said, feel free to ask questions also in the chat already. But we will first do the two presentations, and then they can answer any questions later. So Janik and Mario, the floor is yours.
Thank you. I think Janik will share the screen. All right, perfect. So welcome to this presentation of our master thesis about analytical modeling and experimental vibration testing of a novel tuned mass damper Before starting, we would also like to thank the SGEB board for their support and for giving us this stage to present our work. And with that said, to a quick introduction and the context, the basic idea we had is to prolong the longevity of wind turbines by reducing vibrations induced through wind, earthquake, or like anything else really. This is done by using a tuned mass damper attached to the nacelle on top of the turbine. And so for those of you who aren't familiar with the setup on the Hünkerberg, we'd like to quickly show the most important parts. In the Bauhalle, we have a scaled wind turbine that sat or still sits on a hexapod to induce frequencies. And on the left, you see this turbine. I used Janik for scale here, so you see how big it is. And in the middle, you see the massive hexapod, which can precisely induce vibrations. On the top right, you see the damper with its damping units. Right now, there were only 2, but it can be scaled to 4 or 5 or anything really. And the units are filled with weights as seen on the bottom right and are attached to the frame with springs, and then these boxes with weights in it can slide back and forth on bars. And so the basic idea is that if the right springs and mass combination is chosen to match the eigenfrequency of the system, they can vibrate in anti-resonance and passively dampen the system's response. So this is just the basic idea, and now over to you, Janik.
Yeah, then to our objectives of our project. The main objective was to tune and model a mass damper installed on this scaled wind turbine to certain frequencies so that vibrations and their induced stresses can be reduced. And in order to reach this goal, we have created in a previous project a simple mass spring model of the turbine, including the damper. But however, due to its simplicity, this model did not precisely capture the dynamics of the physical wind turbine. And therefore, we decided to create a much more accurate model with the direct stiffness method. And this DSM model should simplify or help to be able to fine-tune the mass damper in the future. To actually tune the damper, we had to go through the ongoing cycle on the right in the slide. And our goal was to enhance the whole process by focusing on the step of predicting the dynamic behavior of the turbine itself. Now a short review of the results from our project we did before our master thesis. I'll quickly show some data observations and previous models that build the foundation for our final DSM model we did in our master thesis. Previous experiments have shown the following eigenfrequencies, and based on them, we have built our MATLAB model. So the most important ones are 1.1 Hertz for the tower and 5.0 Hertz for the blades. And in our project before the master thesis, we have created a simple 2 and 4 degree of freedom mass spring model with and without the damper. And because this approach was too simplified, the resulting eigenfrequencies were a bit off, with 1.4 Hertz for the tower and 4.7 Hertz for the blades. And there we decided to create the 3-dimensional direct stiffness model. Then in the process of writing the DSM code, we gradually increased the complexity of the model by only modeling a cantilever beam in the beginning, and also increasing the degree of freedom per node from 2 to 4 to finally 6 degrees of freedom. And by that, we minimized the number of potential errors in the process until we reached the final model layout here on the right. Then we structured the DSM model by defining all input parameters, the discretization, and then the stiffness and mass matrices are assembled and the boundary conditions are applied at the end. After that, the modal analysis could be done. Then for each element are all material properties, geometry, and the desired number of elements defined in the beginning, and based on that, the coordinates of each node and their connectivity are defined. On the right, you can see that we divided the turbine into 6 components: the base, the front and back of the nacelle, and the 3 blades. And here you can see the mass and stiffness matrices we used. All elements in our model are a 2-noded Euler-Bernoulli element with 6 degrees of freedom per node. And to assemble the mass and stiffness matrix of the whole structure, we created an assembly loop that goes over each element, and for every current element in the loop are the local matrices defined, and then based on their connectivity and coordinates are they rotated and assembled to the final system matrices. The 12 by 12 transformation matrix is computed using the rotation matrix R, with the order of rotation being Z, Y, and then X, and those angles alpha, beta, and gamma were therefore predefined according to that rotation order for each component. And during the process of creating the model, we used several methods to check if we are on the right track. And a very useful one was to check the static displacements for an applied unit force on different locations on the turbine. And here you can see some examples, and it appeared that all components deformed as expected. Now to the modal analysis of our model. In the right figure are the plots of the first 9 mode shapes of our MATLAB model. The first one, for example, is the first tower mode shape in global X direction, and the second one in global Y direction. So the most important ones are these in global X directions because our known eigenfrequencies from the experiments also come from a unidirectional excitation. And for the experiments, we tuned our 2 damping units Mario showed you in the beginning to 1.1 and 5.2 Hertz to target the tower and the blades vibrations. Yeah. Then here on the left, you can see the frequency response function for our direct stiffness DSM model, and with and without the tuned damper units. The blue graph represents the model with the damper, and the red dotted graph the model without the damper. The other 2 graphs are for each damper unit. And if we take a closer look to the zoomed in picture on the right at 1.1 Hertz, you can see that the model with the tuned damper, including with the damper included, shows 2 peaks next to the original peak from the model without the damper at 1.1 Hertz. And this indicates that the targeted eigenfrequency is indeed mitigated by the tuned mass damper. However, the tuned mass damper that targeted the blade's eigenfrequency at 5.2 Hertz did not induce any significant change in our frequency response function or in the graphs. Yeah, and now to you, Mario.
Thank you. All right. Since the first data set, which Janik mentioned, the one which was collected in another thesis, was very important for creating our model and more or less achieving the correct natural frequencies, a second set of experiments had to be carried out to collect data with which we could validate the theoretical model. And so the same data set was also used to tune the model to the most recent version of the wind turbine, which, for example, does not hold the original rotating mass, which induced a unidirectional vibration anymore. And this makes the whole model less heavy and makes it more symmetrical, and was therefore more or closer to the real thing. Also, during the second series of experiments, the effectiveness of the damper was tested. And here you can see the different tests which we carried out, but I won't go over all of them in detail. But just quickly on the left side are all the excitations we did with steady frequencies for the locked and unlocked state. And on the right are the sweeps which we performed. And as you can see, in the unlocked state, we had to do many sweeps until we found the ideal acceleration that moved the damping units. In the unlocked state, we had to do a lot of different sweeps to find the ideal acceleration that moved the damping units in the damper, but did not go as far until they touched the walls of the damper, because that happened when we induced something that just engaged so much that they touched the walls, and so we had to go really far down with the input. And so just quickly to mention, not all experiments which we did were recorded. Some were simply carried out for validation by eye, just to get a feel of the whole system. So firstly, we'll look at the results from the system with a locked damper. The graphic shows the frequency response function for the sweep performed on the physical system with the locked damper. And the frequency on the sweep reached from 0.5 Hertz to 16 Hertz, so 5 octaves. And the system was excited with an acceleration of only 0.025 Gs. The dominant peaks lie at 1.1 Hertz, 4.4 Hertz, 5.2, and 11.3 Hertz. To fully understand these peaks, it's important to again mention that the accelerometers which were placed on the turbine were only placed in global X direction of the turbine, which happens to be the direction of excitation as well. And therefore, eigenmodes out of plane or rotational eigenmodes don't show dominant peaks here. Now let's compare the data FRF to the model FRF. The first question is, was the model accurate enough to be used for further cases? So on the left, you can see the plot which we just discussed. And in the middle, you see the FRF created by the model, also in global X direction at the node where the accelerometer would be placed. And as you can see on the graphic on the right, the difference in the frequency at the dominant peaks is fairly small. And at the frequency with the biggest tower deflection at 1.1 Hertz, the difference was only 0.05 Hertz, which is very good news. The first blade eigenfrequency was off by 0.41 Hertz, and the second one, which was also the one of the two frequencies was originally tuned to, was only off by 0.01 Hertz. The second tower eigenfrequency at around 12 Hertz was off by 1.6 Hertz, and this sounds very high, but considering the high frequencies it oscillates and some uncertainties, we think it is already pretty close. So now that we've shown that the accuracy of the theoretical model was close enough, we tried the correct damper configuration and recorded the response of the physical system. So here we'll see the most important results from the system with an unlocked damper, so moving masses, and discuss the changes it had on the system. This is the FRF of a sweep with frequencies from 0.5 Hertz up to 16 Hertz with only 0.005 G's acceleration. And here the acceleration is 5 times smaller than what we saw with the locked damper. And as already mentioned, this was because the damping units touched the damper walls while engaging at higher accelerations. And so we had to tune it down. And the FRF looks fairly similar to the FRF with locked dampers, with peaks at similar positions as well. So not a lot found out here. But now we'll look at the damper's effectiveness at different frequencies by comparing amplitudes. Firstly, the most dominant eigenmode, the tower's first eigenmode at 1.1 Hertz. On the left, you can see the acceleration signal at the top of the tower with the damper locked. And on the bottom row, you can see the absolute values of the maximum and minimum acceleration in the steady state. In the middle, you see the signal at the same accelerometer with the damper unlocked. And these two graphs are scaled the same, so you already see the large change in acceleration compared to the locked damper. Finally, on the right, you see the two plots laid on top of each other showing the difference the damper made. And the acceleration could be reduced by 70% with the damper active, which is quite a lot, and for us also a nice result to see. Here you can see a video of the locked and unlocked system at 1.1 Hertz, just to get a feel for it. So on the left is the locked. You see very large deflections. The video goes, yeah.
It's a bit laggy, I don't know.
Okay, sorry for that. And on the right, can you show it again, Janik, the unlocked? Yeah, here you can see that the 70% which were dampened. So before it had huge deflections, and with the damper active, it only moved a little bit. Of course, with the stiffness of the whole system, it still looks like a lot, but the difference is what is important here. Okay, thank you. So next, we compare the effectiveness of the damper at 5.2 Hertz at the tip of the bottom blade, which was also a goal for us to also reduce the stress on the blades. On the left, again, you see the system's response with a locked damper, in the middle with an unlocked damper. And already the plots look very similar. And when you put the two on top of each other, which can be seen on the right, we see that the damping is not very high. The effective reduction of acceleration lies at 0.1 volts, and compared to the locked state, the acceleration was only reduced by 4.5%. And it's still reduced slightly, but it's not anywhere near the reduction we saw at 1.1 Hertz at the top of the tower. And so now we want to compare the influence of the damper again at 5.2 Hertz, but not at the tip of the blades, but at the top of the tower, as you can see on the top right-hand corner of the slide where the accelerometer lies. The tower shakes as well from the resonance that the blade experiences, and these accelerations can be attenuated by the damper. On the left, again, the undamped, and in the middle, the damped signal. And as you can see on the right-hand plot, the damping looks quite big. In fact, the signal is reduced by 14%, which is 3 times as much as the attenuation recorded at the blade. And so we asked ourselves, why could that be? And we came to the conclusion that it has to do, of course, with the placement of the damper. And since the damper sits right next to the tower, it also has its biggest influence there. And if we want to dampen the signal at the blade in a similar percentage as for the tower at 1.1 Hertz, the damping unit would have to sit closer to the blade's tip or along the blade somewhere. So this result, however, is still nice to see because it shows that the damper is also able to reduce strain on the tower at higher frequencies if tuned accordingly, while simultaneously operating at a second eigenfrequency, like in this case, 1.1 Hertz, just with 2 different configurations in the sliding masses. Yeah, here you can see the damper engaging at 5.2 Hertz. Maybe if it's, yeah, if it's laggy, it can't really see it, but they just go back and forth really fast. So I think we skipped that, Janik. Oh, no. Yeah, there you can see it. Okay. So now we just wanted to mention a few general remarks and observations we've made. Firstly, the damper works very well when the system balances itself out after the excitation stops. We saw that with an unlocked damper, the system comes to a halt much faster after the last vibrational input. This shows that the damping ratio was increased considerably. And this makes total sense, but it was still impressive to see just how much faster the system stopped oscillating compared to when the damper wasn't free. And secondly, by eye, we were able to detect eigenmodes at eigenfrequencies, which we didn't excite on the hexapod, which matched with the model's predicted mode shape. So like rotational or horizontal, different ones, which we saw in the theoretical model, but couldn't excite on the physical model. But sometimes they still kind of showed up, and it was just nice to see that those were somewhere represented. And now to a quick conclusion of the whole project. From the results, we conclude that the model depicts the physical scaled wind turbine sufficiently accurate. And we saw that the eigenfrequencies mostly match. At some frequencies, they were spot on, and at other frequencies, they were just slightly off. The shape of the FRF was also very similar and showed dominant peaks at the same frequencies. And lastly, concerning the validation, the mode shapes seem to match pretty accurately, which is a good sign that our theoretical model behaves very similar to the physical model. Then on to the damper. We saw that the damper works exceptionally well at 1.1 Hertz, which is a great result since this is also the mode shape with the largest deflection at the top. But since the deflection is large, the damping unit also has to travel a very long distance. Therefore, longer rails, as we suggested already in previous work, would be a nice addition. But then there comes in the question of reality, like would this be possible on actual large turbine to have such long rails for the masses to move around in? But for this model, it worked, and we would have to have longer rails for them to work perfectly. And then one thing we were also glad to see working was the damper was tuned to 2 frequencies and was able to engage at both frequencies without changing the setting on the damper and only changing the input frequency on the hexapod. This confirms that for a used case, a tuned mass damper could hold a variety of different damping units tuned to different eigenfrequencies, and depending on the input, which is mostly random, they could all be dampened individually at the same time. And so in the end, we now have a model where any properties of any wind turbine can be plugged in, and the eigenfrequencies and eigenmodes will be calculated and shown in our model. And from here, with basic Excel calculations, the mass and spring combinations can be found to dampen specific frequencies on the actual turbine itself. So yeah, this was it. Thank you very much for everyone who tuned in. And if there are any questions, we're happy, or we hope we can answer them. Thank you.
Thank you very much also for this very interesting presentation. I think we got 2 questions. Well, one is more like a comment to both of you for the nice presentations, and to SGEB for sharing the webinar. Well, thank you for tuning in, I would say. And then there is we have one more question by, I'm not sure, it's an acronym, RH Fellers. I'm not sure if you, yeah. So, or if you want to ask, it's a question to Caroline. Sorry. Whether the tower is more rigid than the nave head of the church, or whether it's the other way around.
Yeah, I can answer this. So actually, the nave of the church is more, so nave, as in the whole body of the church, is more rigid / when you can just consider the entire, also the church body with the bell tower, just like the church as it is more rigid than isolating just the bell tower, which we can see indicated in the periods. So the period of the whole church is smaller than the period of just the bell tower, which indicates that proportional to its mass, even as the mass of the whole church is included, it's much more rigid, which is going to decrease your period. So that is why the bell tower is actually much less rigid than the body of the church.
Thank you. Are there any? Okay, yeah, thank you. So, are there any other questions? You can also raise your virtual hand or just turn your mic on if you want to ask any questions. Otherwise, I would have a few actually, but I was also noticing we're running a little late, or not late, but I unfortunately I have another meeting at 1 also, so I need to really stop on time. But I really want to thank all three of you for first of all, I mean, congratulations for the very nice work. It's really interesting. Also, it's always interesting to have some somewhat different topics. So, and thank you very much for the really insightful presentations. I enjoyed a lot. Then maybe from my side, one more announcement. So we have our next webinar on the 20th of May, also at lunchtime. It's going to be in French about questions juridiques, so like legal questions rising with earthquake verifications and so forth, in which context, within the context of Switzerland, obviously, but also legal obligations to perform verifications or not when you want to do renovation, surélevation, and all these things. So all the information is on our website. Also feel free to spread the word. I think it's not only interesting for engineers, but maybe also architects, building owners, and so forth. All the information and the link to join is on our website, SGEB.ch. And with that, so yeah, thank you all again. Thank you all again for tuning in also. It's really interesting. And have a nice day, everyone, and hopefully see you next time.
Thank you.
Thank you.
very much. Thank you.